In this video, we're going to talk about the distance formula in 3D space and the equation of a sphere. So let's begin with the distance formula. So the distance formula in 3D space is really similar to the distance formula that we're used to just in terms of x, y coordinates. And let's just state what it is. So the distance between a point x1, y1, z1 and a point x2, y2, z2 is, I'm going to call it d for distance, and it's going to involve a square root, just like the distance formula that we're used to has. And inside it, I'll have the first x coordinate minus the second one squared, plus the first y coordinate minus the second one squared, and then plus the first z coordinate minus the second one squared. And it doesn't matter the order that I do the subtraction, whether I do the first x coordinate minus the second one, or the second one minus the first one, because when we square it, we'll get the same thing regardless. Okay, so I'm going to highlight this. So this is our distance formula in 3D space. Okay, so let's draw a picture. Okay, so when we're talking about distance, what I mean is if I have one point, let's call this one x1, y1, z1. And if I have another point somewhere in 3D space, let's call this one x2, y2, z2, and we connect them. This formula tells us the distance between them. If we want to show where this formula comes from, it's really similar to how we show where the two-dimensional distance formula comes from. We use the Pythagorean theorem, actually. And with the three-dimensional version, we can show it by using the Pythagorean theorem twice. Okay, so in the homework, there will be a problem where you're going to show a version of this. Okay, so that's something to look for. All right, so one of the main applications of the distance formula is we can use it to get the equation of a sphere. So a sphere is the 3D version of a circle. So here's the definition. A sphere of radius r it consists of all points x, y, z. So when I write s dot t dot, that means such that. So this means such that. The distance of x, y, z to the center, which I'm calling x naught, y naught, z naught, is r. So quick comment about notation. When you write a number with a subscript 0, like z subscript 0, this is said z naught. Not as a word that refers to 0. Okay, so conceptually we know this is true. Every point in the sphere, whatever it is, x, y, z, it needs to be a distance of r away from the center. That's what this is saying. But let's write that with an equation. So this is saying that if we take the distance, so using the distance formula, the distance from x, y, z to x naught, y naught, z naught, that would be x minus x naught squared plus y minus y naught squared plus z minus z naught squared. That distance needs to be equal to r. And if we square both sides, we get x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. And if that looks sort of familiar, it's because it looks a lot like the equation of a circle, except now we just have a z variable in here as well. This is the sphere equation. That's actually where it comes from. It just comes from the distance formula. The same thing is true about the equation of a circle. It actually also comes from the distance formula. All right, so I'm going to highlight this as well. All right, so I've gone ahead and highlighted it. Let's do an example now. So this is example 5, continuing the numbering from the examples in the previous videos from this section. So let's describe the intersection of, so the first graph has equation x squared plus y squared plus z squared equals 1, and the other graph is y equals 1/2. Okay, so pause the video at this point for about 4 minutes and see if you can graph both of these things and visualize what their intersection looks like. Okay, 4, 3, 2, 1, pause the video. Pause the video for about 4 minutes and try to graph each of these. Getting this practice, graphing these 3D shapes is super important because this is likely something that you're a lot less familiar with compared to graphing just 2D curves in the XY plane. So really take advantage of this opportunity to practice this problem now. That way you'll already have gone through the process of thinking about questions like this before you see them on homeworks and on quizzes and exams. Alright, so let's go ahead and talk about it. Hopefully you've paused the video. If not, go ahead and do so now and think about this question first. Well, let's go ahead and talk about this. So let's talk about this first equation first. So x squared plus y squared plus z squared equals 1. This looks like a sphere. This is a sphere, and if it's a sphere, I need to be able to tell what the radius and the center are. So r squared is what is on the right-hand side, so that's 1, which means r is going to be the square root of 1, which is 1. So the radius of this is 1. And the center of the sphere is the origin, because there's no numbers written next to the x, the y, and the z. That implies that there are zeros there. The center is, let's just say the center is at the origin in words. Center is at the origin. Okay, so we know what one of these is. What about y equals 1/2? So equations like this we have more experience with from the previous videos of the section. So y equals 1/2 means that x and z are free because they're not described in this equation. And that means we're talking about a plane. Because two of these variables are free, and it's going to be parallel to the xz plane. Because the y coordinate is going to stay constant at just 1/2 the whole way. It'll be easier to see that once we start to graph this thing. So it's the plane parallel to the xz plane with all points having y coordinate equal to 1/2. Alright, so let's start to graph these two. Let's put this in black, or axes, and then I'll describe the intersection. Okay, so z-axis going straight up, x-axis sort of coming slanted, and then y-axis coming out to the side. Okay, and let's draw some negative directions. So I'll go negative going down for the z-axis, negative x-axis going into the board, and then y-axis going to the left. So the sphere is centered at the origin, and then it needs to have radius 1. Okay, so I'm just going to draw something circular, and then I'll do my best to try to make it look 3D, although spheres are challenging, so definitely bear with me here. So this is 1, this is 1, this is 1. Because the radius of the sphere is 1, and it's centered at the origin. Okay, so to make this look a little bit more 3D, I'm going to draw these sort of curves. Okay, and hopefully that makes my sphere look a little bit more 3D, although honestly, spheres are challenging. Okay, and now let's draw this plane where y equals 1/2. So 1/2 is going to be not as far as 1, so 1/2 is somewhere here. Okay, so what I'm going to do now is, the y coordinate always needs to be 1/2, so I need to draw a plane that's parallel to the xz plane. So I'm going to start off by drawing a line through 1/2, through this point that, where 1/2 is on the y-axis. That's parallel to the xz plane, so that's just going to look like a line that's parallel to the x-axis, so something like this, going that direction and then coming forward in this direction. And then at those endpoints, I'm going to draw vertical lines. So a vertical line at this back endpoint, parallel to the z-axis, a vertical line at this front. The front point, let's go a little bit more front, up. And I want this one to have the same height as this one in the back. And if I connect them, I should have a line that's parallel to the x-axis. So I'll erase something, a little bit of that one. Okay, and then let's also extend this down. Let's also extend this a little bit further down. So both of these vertical lines, I'll draw a little bit further down, a little bit further down. And then let's connect those with another line that's parallel to the x-axis. Actually, you know what? Let's just draw a little bit further down. Undo that. Okay, a little bit further down, a little bit further down. Okay, connecting them with a line that's parallel to the x-axis. So I get something like this. So what's going to happen is that plane, because 1/2 is sort of inside where 1 is, this plane, and let's zoom out a little bit so I can see more of the original problem. The plane slices the sphere. Okay, and when it slices it, there's going to be 1 point here, 1 point here. And just if you think about if you were to slice a sphere with a plane, what shape would that make? It would actually make a circle. Again, it's hard for me to draw visually what this would look like. So I have this part that I can see, and there's going to be part underneath that I can't see. So I'll draw that with a dashed line. So it's going to be the circle. Intersection is a circle. It'll turn out it's a circle, but if it's a circle, I should be able to just say things like, what's the radius and what is the center? So let's talk about how we'd get that. So if we want to get the intersection, if we just think about how we get intersections of things with two variables, we do things like substitute one equation into the other. Let's do that here as well. Let's plug y equals 1/2 into the first equation. That'll give us x squared plus 1/2 squared plus z squared equals 1. And if I rearrange this, we get x squared plus z squared equals 3/4. And we can't forget that we still have the condition. Like right now there's no y in this, but y isn't free on the intersection. Y is still 1/2. We can't forget that we have that condition. Okay, but now looking at the fact that it's x squared plus z squared equals 3/4, that's the equation of a circle. That is the equation of a circle. And what's the radius? The radius would be the square root of 3/4, which is √3/2. And the center would be at, so looking at my circle equation, I can tell the x coordinate is 0, and the z coordinate is 0. Thinking about where the center would be. The y coordinate of the center comes from the fact that I know y is 1/2. So that tells me the y coordinate of the center. And moreover, this circle is parallel to, because it lies on this plane, and the plane is parallel to the xz plane. This is parallel to the xz plane. And now we have a very solid description of our circle. So this would be our answer here, but let me also just label in my picture that the intersection is a circle. Now we've actually verified that with some algebra. Alright, so we have completed our last goal for this section. We've talked about the 3D distance formula and how we use that to determine the equation of a sphere.